In this video, we'll talk about how we perform these operations on a max heap. So if we were to implement this as a class or some sort of, encapsulated data type, then we're going to need a few member variables to help us out. One of them would be the array itself that's going to hold all the data, and I'm going to call that heap array. Another is the size of that array in storage. So I'll call this heap array size. And this is not about, this is just about how big the array is that we allocate and nothing more. And then the last field here is next index. And this tells us how many things we've inserted into the max heap. And if we insert another one, where we would insert it. You can also think of this as the length of the heap, how many items are in the heap. And so we'll use this next index that way. Okay, so using those variables, when we start out and we haven't added anything to the max heap, the next index would be 0. And we would need to allocate that array and we would need to set it to be a certain size. Okay, so assuming we've already done that. And next index is 0, meaning the first thing we insert would go at the very beginning of our max heap. Then let's look at some of the code for doing an insertion and doing a removal on a max heap. So when we insert, the first thing we would want to check is that next index is less than the heap array size, because that means we have space. If we didn't have space, then we might need to resize the max heap. And that would work in a lot of the same way we've done resize in other contexts, where we just need to allocate a bigger array, copy everything over, and set next, and basically next index would stay the same. It's just now our array pointer would point to a different location and our heap array size would be bigger. Okay, but then we just move all the data over. But I'm not showing that here. I'm just returning false to indicate a failure, but you don't have to fail. You can make the heap bigger. But let's assume for all the code that we're going to talk about now that our heap array is always big enough. And so in that case, we're going to go into the if statement. And what we'll do is we'll store this data item at the next available slot. Again, for a max heap, this is equivalent to storing it in the next free spot on the last level of the tree. It's exactly the same meaning. So we just set heap array at next index equal to our data to put it in the next available spot. Okay, then we call max heap percolate up, because we might have just inserted into the heap a big value, and it might actually be larger than its parent. So this max heap percolate up is going to do that check of looking to see, is this new node bigger than its parent, and do we need to swap them? But we're just going to call it as a function. I don't have all that code written out here. We'll look at the max heap percolate up pseudocode next to see how it works. Okay, after we call max heap percolate up, then we increment index, then we return true. And so incrementing index just guarantees that we see the heap as appropriate size. Now, depending on how you write this max heap percolate up pseudocode, it might be more appropriate to increment next index before you call that function. For my pseudocode, it doesn't matter very much, but for other implementations, it might matter. So that's something to keep in mind. Once you insert the data, it's there, and then you need to percolate it upward. So how does that percolate up work? Well, we're going to start at the bottom of the tree conceptually. Now it's all an array, but we think of it like a tree, and we're starting at the leaf of a tree, and now we're going to look upward to see, oh, is this value bigger than my parent? And if it is, we're going to swap it. So when we get into this max percolate up, we know we might need to do as many swaps as the height of the tree. To move the biggest item, if we just inserted the new maximum value, we're going to have to move it all the way up to the root of the tree. So we have a while loop here to reflect that this is something we may have to do several times. And so as long as our node index is bigger than 0, we are going to keep going up the tree. Okay, the reason we have this condition greater than 0 is because once we get to the root, we should not continue, right? We have to stop. So that's our boundary condition. If node index is 0, we've reached the root and there's nothing else to do. So while node index is greater than 0, we calculate the parent of our current node. And so the parent, we would use that formula we talked about. It's node index minus 1 divided by 2. And this will tell us the parent. And then we just do a comparison. Is the node index where we just inserted bigger than the value in the heap at the parent index. And if it is bigger, that means the parent, it's bigger than the parent, so we need to swap them. And so I just wrote this function called swap here to conceptually say, okay, whatever's at parent index needs to swap with whatever's at node index. Okay, and then because we might need to do this again between the next two levels of the tree, we update node index to be parent index, right? And now we're going to do this whole process again in a loop. Okay, on the other hand, if this comparison that we did, if heap array at node index is not greater than heap array at parent index, then there's nothing left to be done. And so the else case just returns from the function. Right, now if we did update node index to parent index, then we're going to go back around to this loop. We're going to make sure that that new parent index isn't the root, that we're still at some node, but we haven't quite gotten to the root. And then we try to do the same thing again, where we calculate the parent of that node, and we see if we need to do another stop. We keep doing this until we've reached the top level of the tree. Okay, so that's insertion. Okay, and then MaxHeap remove is our next function we need to implement. And in MaxHeap remove, okay, the MaxHeap remove is going to do the opposite of what the insert did in some sense, right? So with a MaxHeap remove, we only care about removing the maximum value. So we're always going to be taking out the value at position 0. So the very first thing we do is get a copy of the value at position 0, which must be the maximum, and that's what we're going to return from the function. Okay, but then the key part of our work to maintaining the invariant property of the max heap, that the maximum is always at the root, then we have to do a few more actions. So as we talked about in the previous videos, the first thing we're going to do is take the last value in the heap, which is at next index minus 1, and copy that to 0, right? So we go get the very bottom right corner of the tree, the last node in the last level, and we move it back up to the top. And then we percolate down. And percolate down means we look down the tree at its children, and we look to see if any of those nodes are bigger, and then we do a swap. And that's going to happen to max heap percolate down. So we do the swap of the last element to the first element. We decrement next index to indicate the array is one element smaller than it used to be. We have one item less because of the removal. And then we call MaxHeap percolate down, and we're passing in two arguments here, and that is the node we're starting with 0 and the size of the heap. And really, since the size of our heap could be a member variable, we don't necessarily have to pass it into the function. It could just be a class variable, but just for clarity here, I'm passing it in explicitly. Okay, so the first thing we do is we get the value at node index, which at the beginning, this is almost always going to be the root, right? And so we're going to start at the root and start propagating it down. So this is the value we just moved to the root of the tree. And then child index is the index of this, is the first child of node index, right? And we get that child by saying node index times 2 plus 1. And the second child would be node index times 2 plus 2, right? So we're going to need to look at both of those children to decide, can I push this value down the tree to one of its children because one of its children is bigger? Okay, this while loop, while child index is less than size, what this is saying is that while I haven't gotten past the end of my array, right, I'm going to be possibly taking this value I just moved to the root and pushing it back down to the last level of the tree. But the only way I know where the last level of the tree is based on the number of things in the tree, the number of things in the array. And so just checking child index is less than size will do that for me. If the next child index is beyond the end of the array, then that means that there is no such child, right? It means it's at a level that hasn't been filled out yet, and I should stop looking, right? I might have already pushed my value as far in the tree as possible. Okay, so this first loop here, inside the while loop, right? This while loop will just run until I've pushed the value down as far as I can. And then this for loop on the inside, it's saying, well, consider both of the children of this node. And if either one of the children have a value greater than the max value, and we're going to set max value equal to the value of the current position we're considering, right? If max value is greater than, if the value of a child is bigger than the value in the node that we're percolating down, then we're going to remember that max value and we're going to remember that child's index. And then after we get through this loop, we know which child was the biggest child, and we do a swap. And we swap for the child and the node. And this pushes our value down the tree. Or in other words, it pushes the children that are larger up the tree. Okay, and then we move the node index to where the child was, because this value that we just pushed down, it may still not be in the right position, right? It might still have some child that's larger than it. And so we need to keep trying to push it down until we can't push it anymore. So we set node index equal to max index, we calculate a new child index, and we go back around and we try to do this whole process again of pushing this value down the tree. Okay, and that's how MaxHeap works. The MaxHeap remove works. So first, we just swap the value deepest in the tree back to the root, and then we call this function to push it back down into its correct position and let anything move up in the tree that is actually larger. Okay, so what's the time complexity of these operations on a MaxHeap? Well, when we think about percolate up and down, we know that in the worst case, we're going to take a value at the root and push it to a leaf, or we're going to take a value at the leaf for percolate up and push it all the way to the root, right? So that means in the worst case, we might have to move H level of times. We might have to do H moves up the tree, where H is the height of the tree. But since a heap is a complete tree, then that means it always has the minimal height that it can have. And we can express the minimal height as a log function, log 2 of n. And we can ignore the 2 because it's just a constant factor from log n. So big O of h is equal to big O of log n. So what we would say here for percolate up or down is that it has big O of log n. We don't need to say big O of h because big O of h is the same in the case of a MaxHeap as big O of log n. For insertion, what we have to do is first add something to the end of the array and then do a percolate up. And so percolate up is really what drives the cost of insert. And so that means insert is basically just the same cost as percolate up, which would be log n. And then remove, similarly, it's easy to take the heap off to take the max off the max heap, but then you have to do the swap and do the percolate down. And this remove will really be determined by the cost of percolate down, which as we said before, is log n. So remove is also a log n operation. Okay, so in general, this is pretty efficient. We can add things into our max heap at log n, and we can remove them at log n. And so, this is a fairly efficient way to manage a collection of items, a set of items in which all you care about is the maximum. It's a lot better than having an array and sorting it on demand when you want to know the maximum. Okay, so in summary, operations on a heap are efficient and bounded by the height of a complete tree, which we know to be big O of log n. And the other thing I would say is that the same algorithms can be adapted to a min heap. All we need to do is change the conditions from finding the max to instead finding a minimum.